All right, everybody. Hello and welcome back. Welcome to another fantastic episode in our trip and looking at the all of the wonderful things that make up our Earth system. And today we're going to start talking about some of the really dry places on our planet. Those are our deserts. We're going to talk about today, our objectives for today are to talk about deserts, describe what makes a desert, describe where these deserts occur and why, and then describe some of the features that we see in the desert. So hold on tight, right? This is going to be a fun ride. So here we go. In talking about our types of deserts or our desert protocol to say, first thing to note, and very important to note, is that we're not talking about dessert, we're talking about deserts. And so just as a matter of practice, dessert has two S's in it, desert has one. One way to remember that is you always enjoy maybe two helpings of dessert, but a trip to the desert every once in a while is about all you need. So one S there with the desert, dessert, you get two. I love the desert, and I've spent many days in the desert doing research as well as for recreation. It's a remarkable place, and one of the remarkable aspects of the desert, what makes it so unique, is that it is an environment on land here where things are hot, dry, and also sometimes cold. Temperature fluctuates radically in the desert. Precipitation levels can fluctuate radically in the desert. In general, deserts are defined as places that experience less than 25 centimeters of precipitation per year. So less than 25 centimeters of precipitation per year. But it's important to recognize that oftentimes that precipitation comes over very short windows. So that's not just, every month we get a few centimeters of precipitation. That is, a single storm event may bring all of this precipitation for the year. And so, a really interesting thing there to think about is the desert's ability to absorb that water and utilize that water, with it coming all at once oftentimes and still in very small amounts. So we see lots of vegetation adapting to limited rainfall throughout the year, as well as a landscape that is etched and carved and shaped by these periodic, what we're going to learn, are flash flood events. And so we see that the majority of our deserts actually occur at a pretty specific distance from the equator. That is about 30 degrees latitude. Now, we call these latitudes the Tropic of Cancer and the Tropic of Capricorn. 30 degrees latitude refers to about a third of the way from the equator to either pole, right? So again, that equator, 0 degrees latitude, the North and South Pole, 90 degrees latitude, north and south. And so 30 degrees latitude is about 1/3 of the way from the equator to the pole there. And we see a lot of deserts along that 30-degree latitude line, right? And why is that? Well, that's in part, we're going to learn, has to do with atmospheric circulation. And so we actually have four main types of deserts. We don't only find these things at 30 degrees latitude, we find them all over the world. And so again, looking at applying that 25 centimeter per year threshold, right? We see that we can have multiple different types of deserts in addition to the abundance of deserts that we see at that 30 degrees latitude. So we have deserts at our poles, right? Polar deserts. And so that's a sarcastic comment there, in this being a tricky one. Polar deserts occur at our poles, at the North and South poles. So you think, well, Savagil, there's a lot of snow and ice at the poles, isn't there? So a lot of water, right? Well, yeah, that's because that water sticks around for a long time, though it doesn't fall all that often, right? So again, that 25 centimeter threshold. We also have these things called rain shadow deserts, and these are associated with a topographic feature. So a great example of a rain shadow desert is Death Valley. When we're talking about topographic features, what we're talking about there are things like mountain ranges, right? So we're going to learn that mountain ranges can block moisture from getting over them and resulting in the downwind side of those mountain ranges oftentimes being very dry. This is something we call the rain shadow effect. We're going to talk about this in a little more detail. And then our inland deserts. Inland deserts, that just means far from the ocean. And so when you're far from a major water source, right, we know that to get rain, we got to have that hydrologic cycle, right? Evaporation, condensation, precipitation on my mind. I'm not a singer, but we know we need all three of those parts, and the necessary ingredient there is water. So if you are far away from water, you're going to have a hard time with starting up that hydrologic cycle, right? So areas far from the coast, oftentimes very arid, very arid. The interior portions of Australia would be a great example of that. And then western coastal deserts. Western coastal deserts, when we look at circulation in the ocean, we see that the western margins of most continents are typically pretty dry. And that's because the nature of ocean circulation, right, results in cold water being present along those western coastlines there. And so that cold water, again, our evaporation, condensation, that evaporation, if I were to ask you, if I were to give you a bucket of water and say, can you evaporate this bucket of water, please? You would likely say, okay, I want to do that as quickly as I can. So one of the things I want to do is heat it up, right? I want to heat up that water because cold water isn't going to evaporate as quickly, right? And so when we've got off the West Coast here, mostly cold water, that cold water comes from well north of us here in Southern California. And that's the same for other western margins in the Northern Hemisphere. In the Southern Hemisphere, those western coastlines also get cold water from near the South Pole, and such that cold water, right, has a hard time making its way then into the atmosphere. Wind and those sorts of things can help pick that limited moisture up off the ocean and concentrate it. And thus we get some big storms during our wintertime, right? But oftentimes our west coast of our major continents, that is those margins located in the eastern portions of our ocean basins, oftentimes pretty arid areas. And so when we look at here, the way the atmosphere circulates, right? And we're going to give you the really sort of quick version of this. Circulation of our atmosphere is the atmosphere's attempt to take energy from near the equator, this surplus of energy there, and push that energy to the poles where it's very cold, where the amount of solar radiation there is relatively limited. And in making that journey, that atmosphere, the gas, it's moving to the north and south from the equator. And as it's doing so, its motion, its relative motion is impacted by the rotation of the Earth. That is, the Earth is rotating at the equator around, or near the equator, around 1,000 miles an hour or so. That Earth is rotating there, and that spin of the Earth results in this atmosphere on its way towards the pole. It ends up turning to the right in the northern hemisphere and to the left in the southern hemisphere. This is something that we call the Coriolis effect. And the Coriolis effect gets so pronounced in our atmosphere that about a third of the way from on its journey from the equator to the pole, it actually turns around on itself. And it actually does this 3 times on the way from the equator to the pole. So what we see are 3 atmospheric circulation cells here. 1, 2, 3, right? 3 atmospheric circulation cells there, where we oftentimes get weather and dry areas at the interface between these cells. That is where you have warm air rising off of the ocean, right? It's going to carry with it lots of moisture. You're going to get lots of clouds. And so surrounding the equator there, lots of clouds, lots of moisture, right? So we see our rainforests and things concentrated in these areas. We move north of there, we see here at about 30 degrees latitude, you guessed it, the opposite. That is at about 30 degrees latitude or so, what we have is now relatively cool, dry air that starts to sink and converge on itself. And that falling dry air has limited moisture in it. And so what we get is this permanent, what we think of as a high pressure system, where the atmosphere is descending onto the Earth's system or on the Earth's surface there, right? That descending cold, dry air means permanent, right? Or relatively constant dry conditions, right? And so we see here at about 60 degrees latitude, we get some cold air and then some warm air kind of mixing together here. And we actually get some really strong winds and some storms at this interface as well. But that 30 degrees latitude where we've got that cold descending dry air means very little opportunities, very few opportunities for rain. And so when we look at that 30 degrees latitude mark here, that's where we see our largest deserts. That's where we see globally these stripes of deserts across our planet. And these conditions here at about 30 degrees latitude can certainly be exacerbated, made more pronounced, right, if they're juxtaposed with other elements that we discussed. That is, if you're at 30 degrees latitude and you're also far inland, then you're likely going to get very low levels of precipitation, right? If you're on the western margin of a continent and you're at 30 degrees latitude, also likely to be very dry. And so coupling of these factors can really make that dry condition more significant. And so through the Sahara, right, is certainly one of these 30-degree latitude type deserts, and in portions of the Sahara, most certainly coupled with some of these other factors. All right, as always, any of this, I want to pause just for a minute, any of this, if you have any questions at all, or you want to dive in deeper, what's with that atmospheric circulation thing? I want to hear more about that. I've got some maybe other hypotheses that I'm thinking about with that, or, you know, I just want more clarification, or, you know, I want to get more in depth in the Coriolis effect, any of that stuff, right? It's what I'm here for. I love those discussions. So please don't ever hesitate to reach out and let me know that you need that assistance. I'm more than happy to help. All right, let's talk rain shadows. Let's talk rain shadows, our rain shadow deserts. So here in California, right, we've got this active plate boundary, right, cutting through the state, the San Andreas Fault. And there's a whole bunch of faults all around it that lift up some tremendous mountain ranges in our area, right? The source of our moisture in the state, the limited amount of rain that we see there, particularly during the winter months, it comes off of the Pacific Ocean. So it's coming from west of the western margin there. And so that those storms, interestingly, here in California, are storms, because they're coming off of often a cold ocean, they stay at a relatively low elevation, which means that as they move on to the terrain, right, as they move on to the terrain, they have to go over that terrain if they hope to make it further inland. Well, air does an interesting thing, right, if you lift it, right? If you lift it, as you take the air from sea level, right, and you lift it up the face of a mountain range, that air will cool. It will cool. It will cool because atmospheric pressure is decreasing, and you get temperature change associated with that decrease in atmospheric pressure. That temperature change is called adiabatic temperature change. ADI, ABI, ATIC, temperature change, adiabatic temperature change. So as you lift that air, right, less pressure, temperature goes down. You'll experience this if you ever take a drive up to the mountains, right? You go to a place like Big Bear. As you drive up the road, you can maybe feel that pressure change, that decrease in pressure inside of your ears, right? You can feel that pressure. It's kind of building up inside there. and then you have to, pop your ears or something to get yourself to equalize to that lower pressure that's around you, right? And similarly, when you come back down the hill, you feel that increase in pressure. You got to do the same, right? So you're feeling those pressure changes, but you can also feel the temperature changes on any given day. Typically, right, temperatures in Riverside are going to be much higher than they are in a place like Big Bear, right? And so again, that's that link. There's pressure changes and those temperature changes. That's why. And air, as it cools, right, as that air cools, it's able to hold less and less moisture, right? So that air, as it's cooling, it's not able to hold that water vapor in that vapor state. So what happens? Well, that vapor condenses to form clouds. And so as that air is rising, clouds are forming, right? And eventually will produce rain. And that typically will happen on what is called the windward side of our mountains. So again, these storms, they form these clouds on the windward side of our mountains, and then they release all that rain, right? They get rid of all that moisture. And then by the time the air gets over those mountains, it's lost all of its moisture, right? So that air also, as it goes over the mountains, not only is it dry, but as it races down the other side of those mountains, right, it'll warm up as well. That water will, or that air will warm back up as it's recompressed and enters then that basin floor. So the Sierra Nevada mountains here in the eastern portion of California is a magnificent rain shadow. Captures all sorts of rain, right? If you take a drive up the west side of the Sierra Nevada mountain range, you visit places like Kings Canyon or Sequoia. It looks very different than if you visit the eastern side of the Sierra Mountains and visit places like Lone Pine or Bishop, right? And that's because of this dramatic rain shadow effect, right? We have this here in our area, or in a little closer to home here in Riverside. We have this, the Santa Ana Mountains there, right behind places like Corona and Temescal Valley, down into Lake Elsinore, Temecula, right? We have this, what are called the Northern Peninsula Ranges there. They shut up into our area, and they trap a lot of moisture that would otherwise make its way off the coast into our area, right? They keep that moisture there, right, in places like Orange County because of that huge topographic feature, right? And so they also contribute to the dryness that we have in our area here, being on the leeward side of that mountain range. That is the rain shadow effect. And it's a really significant one. We oftentimes see deserts behind these rain shadows. Topography can have a huge impact on precipitation patterns in any given area. But again, one of the interesting things that deserts can most certainly do, is you can have precipitation over a relatively high levels of precipitation over relatively short periods of time. So what does that mean, right? That means that you can have relatively dry conditions, and then all of a sudden you get these massive thunderstorms, right? Absolutely massive thunderstorms. Thunderstorms, we see them here in Riverside County and San Bernardino County most summers, right? Day starts out, it's a beautiful day, blue skies. Maybe you look off in the distance, and early in the morning, you might see one small cloud hovering above San Gorgonio there in the San Bernardino Mountains, or out over the San Gabriel Mountains there. And throughout the day, as the day heats up, you see that cloud grow and grow and grow and grow. And then suddenly, maybe midday, your phone goes off and it says flash flood warning, right? You're thinking, it was beautiful this morning. What happened, right? What happened? Well, what happened is a thunderstorm developed. And the way these thunderstorms develop is when we get high levels of moisture coming off of the ocean or the Gulf of California, down there off the Baja Peninsula, inside the Baja Peninsula there, you can get huge levels, high levels of humidity, bringing huge amounts of water into our area and in really hot air. So that humid, warm air hits our mountain ranges and starts to rise. As that hot air condenses, or the water vapor in that hot air condenses to form clouds, that process releases energy. And so what happens, that hot air continues to rise and release more and more of its water vapor, right? More and more of its water vapor, and you get these towering thunderheads that eventually will collapse, in a sense, in on themselves and dump that water, that moisture over a really short window of time. And in the desert, this is a big deal because that water runs across the landscape relatively quickly. And that's because there's very limited vegetation. Things like grass, plants, trees can soak up a whole bunch of water and slow it down, whereas soil, rock, right, does not do so much of that soaking up. So you get lots of runoff. And that runoff will typically disappear nearly as fast as it comes, but can reach tremendous quantities, right? And so the primary source, again, for water in the desert is oftentimes these seasonal thunderstorms, right? These things really bring so much water to the desert. And again, you get these flash flood events where seemingly dry channels, right, start to flow with water, just as we would see in any other river, right? Sometimes these channels they'll flow even in areas where it's not raining, right? If the rain is falling over the mountain, those channels that come off of that mountain will eventually fill with water. This is why we receive those flash flood warnings, even being here, way down here in Riverside, as we see these thunderstorms over the San Bernardino Mountains, right? And that's because, again, that water will flow and it can be huge volumes of water. But really interestingly, again, that water can disappear nearly as quickly as it comes, right? It runs off into these channels, runs down towards the ocean, and eventually dissipates. So these are some great pictures here of a wash in Phoenix. There we see the wash at about 10:30 a.m., right? That wash about 2.5 hours later, you can see has largely dried out, right? That water is gone, right? That water is gone. And so these flash floods and the flash flood warnings that we receive are super important to understand and to appreciate because they are real. You know, if you're ever out camping, right, you always want to be mindful of the weather. But if you receive a flash flood warning or you're concerned about potential for flash flood, you do not want to be camped anywhere in a channel or in a place where one of these or something like a small canyon where that water can be concentrated over a very small area, right? Because these things can come very quickly and in areas, again, that can be far from where the actual thunderstorm is taking place, right? But again, the desert itself is adapted to this behavior, right? To these weather patterns, right? The plants, the animals, right, are evolved in a sense to deal with water coming in huge amounts and then huge delays before you might see that water again, right? And so again, this landscape carved by these processes have been specially adapted to deal with them within elements of the biosphere. So let's talk about a few of the things that we see in the deserts. As with everything, right? Science likes to name things, and we have names for a bundle of these features that we see out in the desert. And these are a few. We're going to see a few more of these, or we're going to see a few of these in images too, but I wanted you guys to up front have these definitions. So a playa is a dry lake bed. A dry lake bed, that is a playa, right? So a dry lake bed. So again, these lakes may periodically fill with water and then dry out, right? So that periodic drying out, dry lake bed, you got yourself a playa. Bajadas and alluvial fans, right? Bajadas and alluvial fans. So alluvial fans are these fan-shaped accumulations of sediments that often form near the base of a canyon, at the base of a mountain range, as it spills, those sediments spill out onto the valley floor. A bajada is a collection of these alluvial fans that are all right next to each other. They will collect to form a bajada. And we're going to see again images of each of these things. Inselbergs. So lots of sediments moving all around in the deserts, right? Lots of sediments. And so those sediments can accumulate around mountains and small hills to the point where as the basin fills, the very peak of the mountain may be the only thing sticking out of the ground. That's what we call an inselberg. Right? So we can think of these as kind of like mountain island, right? Mountain island. And then we have plateaus, mesas, and buttes. And so each of these are flat bits of terrain. These flat bits of terrain, oftentimes dictated by geological conditions. That is the nature of the rocks, right? The layers of rocks. You may have more resistant, a more resistant layer of rock within the strata surrounding an area. As that resistant rock erodes, right, it's going to erode to form these plateaus, mesas, and buttes. The differences between a plateau, a mesa, and a butte is simply that these are relative to each other according to their size. So a plateau is very large, a mesa is kind of medium, and a butte is our small flat area. And we'll see how that forms because these things can also be related. So here's a few images from your textbook. It's specifying the basin and range here in the western third of the U.S. interior here, or through the North American interior here. That basin and range, right? What we have are repeated mountains and valleys. So lots of rain shadow effect. It's also inland. It's also near that western margin of our continent, right? So it's a very dry area. It's got all of these factors, right, that are dictating low levels of precipitation in this area. And so we see here in the Great Basin, we find things like dry lake beds in each of these valleys here, these grabens, right? In each of these valleys here, we see these dry lake beds, right? Sometimes full of water, oftentimes not. Again, near the base of our mountain ranges, right? We might see alluvial fans. And as those alluvial fans coalesce here in this situation here, this is what we would call collectively, we would call this a bajada. As this continued to fill with sediment, right, or in areas where maybe more sedimentation has occurred, you might see small peaks of mountains sticking out of the ground, as you can see here in this little cross section here, and then what's being pointed out there, that's our inselberg. All right, so let's take a look at some real pictures of these things, chiefly bajadas and alluvial fans in our inselbergs here. And so here we see this great aerial image from your textbook there. We've got this mountain range sitting off in the distance, and we notice there's not a lot of vegetation on it, which means that when these storm events occur over these mountain ranges, you're going to get lots and lots of erosion, right? Lots and lots of erosion relatively quickly. So those storms fall, they break down that rock. That rock is then going into these canyons and moving its way downhill due to gravity to be deposited eventually on this valley floor. So the way that sediment does that, right, is that sediment again is making its way right down this canyon here. And as it exits onto the valley floor, it's going to find its easiest path, right, to the valley floor, right, or towards it. And so what you're going to get is a collection of sediments, right, like this. And so that collection of sediments elevates the topography in that area. So the next few sediments that come through here, right, they're going to go, okay, I'm coming down the canyon here. Oh, it's a little easier if I just go kind of this way. And so they're going to make another lobe of sediments, maybe like this, right? And then the next bit of sediments are going to make their way down the canyon, and they're going to go, oh, this is a little easier going this way, and they're going to make a lobe like this. And the same things are happening in these canyons over here, right? Where they're creating lobes here and lobes here, right? So what you're seeing is this fanning outwards shape, right? Which collectively makes this, right, big alluvial fan, right? So there's one of our alluvial fans. There's another one, right, kind of nested in here, right? And then there's another one over here, right? Right? And so we've got there, and we can see more off in the distance as well. We've got there multiple alluvial fans extending from the mouths of these multiple canyons. And so as these things come together, that's what we call then a bajada. So these are individual alluvial fans. Collectively, we would refer to this as a bajada. All right. So that alluvial fan formation, those bajadas, important concepts again. And if you need me to go through those with you, again, I'm there. Just reach out to me via email or office hours or whatever works for you, and we'll get you taken care of. All right. Cool. Well, let's look here then at an Inselberg. We actually see a number of these in and around Riverside and San Bernardino counties. You might recognize structures that look like that. We do see them here locally. And you might remember from our talks of weathering and erosion, this looks like some spheroidal weathering in there, right? We got some spheroidal weathering resulting in these rounded boulders and maybe some precariously balanced rocks there. But what we're seeing there is just the peak of a mountain sticking out of the ground, right? We're looking at just the peak of it. Underground, there is a buried hill or mountain. Here we're seeing that Inselberg or that island mountain sticking out here in the desert because of those high sedimentation rates in the areas surrounding this structure. All right. So it's not just about sediments being deposited, right? It's that we've got a bunch of loose sediment that likes to move in the desert. And it likes to move so much, that actually the wind can help in that movement. Wind erosion is significant in the deserts. It's significant in the deserts. We see, you might have driven through maybe the Coachella Valley or through Death Valley and experienced when the wind gets really high, you can have some really significant dust storms. And those dust storms, those are moving sediments, right? Those sediments can move because, again, that lack of vegetation, there's no plants there to keep that stuff in place, or very few plants there to keep that stuff in place. So the surface of the desert can change and does change all the time. And so we're going to talk about blowouts in this process of deflation, or what we're going to describe as the formation of what's called desert pavement. All right. So let's look at a blowout. All right. Let's take a look at a blowout here. Blowouts form as that wind moves across the surface and is impacted by small changes in the topography of that desert, right? So that wind may have a little bit of waviness to it. And so as it does so, right, as it approaches that ground surface, it's speeding up as it does so. And in speeding up, it can grab more of that sediment, right? And so what we might see is that in isolated areas, we have this hole created by the wind. And interestingly, the plants are oftentimes specially adapted, right, to deal with this style of erosion. That is, portions of the plant may be buried at times, and that plant will survive, and that plant may be exposed at times. Its root system holding together some aspect of that soil so that it's not completely transferred, right? And so we'll see sometimes in these blowouts in the areas surrounding these plants, these little columns, right? These columns of materials, and that's plants doing what they do to survive given this situation. All right. Another thing, if you've ever been out to the desert, you might have noticed, wow, the whole surface of the desert looks like somebody took a thin layer of gravel and laid it down across the surface, right? So nobody did that, right? That is natural, and that's something that we call desert pavement. Desert pavement. The formation of desert pavement is actually something that's of interest to a number of geologists and people working in the desert. And there's a bundle of theories of how this stuff forms. This is one of them, and the one presented in your textbook is this process of deflation. Deflation. That is, within the desert floor are sediments of all different shapes and sizes and densities. There's a whole mixture of them. And as the wind blows across the floor of the desert, it grabs a whole bunch of sediment, right? It grabs principally, though, in grabbing that sediment, it's going to grab the fine grained stuff, the clays, the silts, and the sands, and it's going to put them in the air and move them with the wind. As it removes those sediments, the surface elevation deflates, right? It goes down. And so what you're left behind with are fewer of those fine grained particles and more of those coarser grained particles. So that process will continue. That will continue and continue and continue until there's no more of those fine grained sediments exposed that can be removed by the wind. And it's at that point that the desert pavement is established, right? And so we can see that the desert pavement must be important because it, in the absence of vegetation, helps to reduce erosion in these environments, right? It is kind of, in effect, sealing the surface of the desert floor there. It's making a seal there, right? That's important, right? For keeping that surface stable, right? And so it's a really important aspect of desert ecosystems. Both plants and animals depend on that stability offered by that desert pavement. And it's really important to recognize that this stuff is very prone to being disturbed. This process of desert pavement formation takes a really long time. So once it's disturbed, it takes a long time to come back, which means that when you're out in the desert, right, it's really important that we do our best to protect this resource so that we can protect the surrounding landscape and ecology. A great example of how long it might take this stuff to return after being disturbed is that out in the Mojave Desert, in preparing for World War II, there were tank training exercises being done by General Patton out in that area. And if you go out there today, still decades and decades later, you can go out there and see tracks from these tanks and these exercises still etched in that desert pavement, right? Those artifacts still there today, right? That's how slow to change this stuff is. And so the next time you're out in the desert, you're thinking, you know, I'm tired of this road. I just want to go cut through those bushes over there across that desert pavement. Or, hey, I want to draw a big picture here by dragging a shovel and moving this desert pavement. Know that that does some damage to the desert floor that can last for a really, really long time. So it's best to leave that stuff as undisturbed as possible. All right. Awesome. Awesome. And so with that, that concludes our discussion here of deserts. Again, what makes a desert? Something with less than 25 centimeters of precipitation, or an area with less than that amount of precipitation. Where do we find those areas? Well, we find those at 30 degrees latitude and or along the western margins of our basins, or in inland areas, or behind rain shadows, right? And then, again, some of these features that we see in the deserts things like alluvial fans and playas and bajadas and our desert pavement and the processes that go into forming each of those things. All right. And again, important to be mindful in these environments. There's a lot, it's a really sensitive ecosystem. And so it's really important to be mindful so that we don't, so that the things we do don't disrupt and permanently disrupt those sensitive ecosystems. All right. So with that said, that again concludes our deserts lecture. If you want to talk about anything in here, please don't hesitate to get a hold of me. It's what I'm here for. I hope that you all are enjoying a wonderful day, a wonderful week. I'll wish you all a wonderful rest of your day. Please take care of yourselves. Be safe out there, and we will talk again very soon. Take care.